All right, so we're going to start chapter 8 with this video. So let me put this in slideshow mode. All right. So chapter 8 deals with angular motion. So far, everything we've done, we've talked about things in terms of linear motion, moving in two dimensions from point A to point B in a straight line. So, what we're going to talk about with chapter 8 is we're going to start talking about things that rotate, things that are not moving in a straight line, but instead of moving in a circle. So, we're going to talk about angular motion, and that's going to include angular displacement, angular velocity, angular acceleration, all of those things, those kinematic things that we had for linear motion: speed, velocity, acceleration, displacement. We have the same things for objects that are rotating, but we use the term angular. And then we'll talk about moments of inertia, torque, and static equilibrium in the other sections. Today, we're just going to deal with section 1. Okay, so let me move this up here so we can move to the next slide. There we go. Okay, so rotation is part of our everyday life. You are rotating at this very moment because you are on Earth, and we are rotating and revolving around the sun, and we're also rotating around our own axis. Okay, so your cars are based on rotation. You think about the wheels and the axles and the different parts of the engine. All of those involve rotation. So we need to understand rotational motion. Okay, so we have to consider position or displacement, speed, velocity, and acceleration for rotating objects as well. Now, before we just looked at those in terms of a straight line Cartesian coordinate type of graph. This time, rather than looking at just a straight line Cartesian coordinate, we are going to look at a circle. Okay, so we're going to still use a graph, but we're looking at it in terms of a circle. And those who are in calculus or pre-cal, you should be very familiar with circles and unit circles and that kind of thing. So it's kind of based off of that. Okay, so let's take this bicycle wheel as an example. All right, if we have this bicycle wheel that's shown, we look at one particular spot on that bicycle wheel and we want to see how far it moves in that circular path. Okay, so here's our reference line. We're always going to have a reference point here at the axle going straight horizontal. That's going to be our starting point. So that would be our 0 degrees. And then as the wheel turns, then that spot is going to be at different positions along that circular path. Okay. Remember that from the reference spot to where the reference point to where the spot is, that is our position, our angular position theta. Okay. So some things that you need to make sure that you write down, none of that just yet. So let's go. To the next slide. All right, so remember that the location of the red spot is its angular position, and that is the angle that it makes with the reference line. The reference line would be an angle of 0. Okay. The sign, these are going to be really important for you to remember because they're going to be worked into the problems. The sign of the position depends on the orientation of the reference line. So if we are counterclockwise rotation from the reference, that means that our angle is going to be greater than 0. If we're at a clockwise rotation from the reference, that means that our angle is going to be less than 0. So you definitely want to write those things down, okay? All right, so usually units for measuring angles are usually in degrees or revolutions. But a more convenient way of measuring that is in radians. So all of our work that we're going to do with angular momentum, or with not angular momentum, with angular motion is going to be in radians. So you're going to want to make sure that you check your calculator and you do have it in radian mode. And again, those of you who have pre-cal or calculus, you should be kind of used to that. So let's look at an example. This piece of pie. A radian is the angle for which the length of the arc, and the arc is the curved part, the length of that arc is equal to the radius of the circle. That's 1 radian. Okay, so that's just the definition of a radian. The radian is the angle for which the length of the circular arc equals the radius of the circle. So here's another comparison where we just kind of broke up our circle. Like I said, if you've done the unit circle before, you kind of have some, you kind of understand a little bit more about this. Comparison between angles measured in degrees and radians is shown here. Notice that at 0 degrees, that would be 0 radians. At 360 degrees, that is 2 pi radians. It is the entire circumference of the circle. Okay. Oops. Did not mean to do that. There we go. So angles are indicated around the circumference of the circle in degrees and radians both. So 360 degrees all the way around the circle, that would be equal to 2 pi radians. That's a conversion that you're going to need to make sure you commit to memory because you'll be using it a lot in different problems. All right. So back to our spot on a bicycle tire example. The radian is useful because it just makes things simple and it gives us a very clear relationship between the angle and the arc length. And that's what we need to make sure that we understand. That when we use radians, that gives us a relationship between the angle theta and the arc length. And this is our relationship. That's one of the first equations that they're going to be using in this chapter. Okay. So if we multiply the radius of the circle times the degrees, that will give us our arc length in radians. Okay. So make sure you have that written down as well. Like I said, I know that for a lot of you, this is just going to be review if you've had this in calculus or pre-cal. But I just kind of want to refresh your memory on this before we start doing problems. So this relationship about the radius times the angle, that only works if it's measured in radians. So make sure you write that down. When we talk about the angle, we're talking about the angle measured in radians, not degrees. So that relationship does not work if you're measuring in degrees. It's why we have to have our calculators in radians for this. Okay. Also, remember this conversion that I pointed out on that circle, that 1 revolution is 360 degrees, which is also 2 pi radians. That's going to be a very important conversion factor for you for when you're trying to convert between radians and degrees or degrees and radians, because a problem may give you the angle in degrees. So, you cannot use that angle in degrees. You're going to have to change it to radians first. And this is going to be how you do that. Okay. So make sure you have that written down as well. Okay, so because we're doing this in radians, you need to remember that the arc length S and the radius R both have units of meters. And since we're doing the angle in radians, it does not have a dimension. So all of these units are going to wind up being meters when we talk about angular displacement. Okay. So just remember that the radians or the angles are not going to have an actual dimension since they are measured in radians. All right, so when we talked about linear motion, we talked about the change in displacement was what was so important. The change in position was what was so important. That was our displacement. Well, the same thing here. So angular displacement is the change in the angle. And the change in the angle is always the angle, the final angle minus the initial angle. So if you started here at this angle, and you then ended up here at this angle, then the change in the angle would be your angular displacement. And that's always going to be final minus initial. Okay, so when they talk about angular displacement, just remember we're talking about the change in the angle, which is the final angle minus the initial angle in radians. Okay. All right, so here is another one of our formulas that you're going to need to make sure that you know how to use. This is the formula for angular acceleration. Remember that I'm sorry, not acceleration, velocity, but linear velocity is just displacement over time. Well, the same thing here. But with angular velocity, we have angular displacement divided by time. So it's going to be the change in the position, angular displacement, divided by the change in time. And our units are going to be radians per second or just per second because radians we don't count it as a unit. Okay. Okay, so the next thing that you want to just probably be easier just to commit this to memory. If it's a counterclockwise rotation, that means your angular velocity is greater than zero. If it is a clockwise rotation, it means your angular velocity is less than zero. And that's going to be really important for determining if your angular velocity is positive or negative, okay? Which is going to determine its direction, okay? So notice that this symbol is called angular velocity. It is not called angular speed. That is because it has a direction that goes along with it in the form of the sign, whether it's positive or negative. Okay, so the sign of the angular velocity indicates the direction, just like in regular linear velocity. The magnitude of angular velocity is called angular speed. So just be aware of that if they talk about angular speed in a problem, they are talking about the number value only of the angular velocity. So let's look at an example real quick. And oddly enough, these are coming back. You never used to find records anywhere. You didn't even have a record player or know what records were for many, many years. But now they're kind of making a comeback. So this is kind of new, but yet old. So an antique long play phonograph record player rotates clockwise. So that is going to be an important thing to remember. At 33 and a third revolutions per minute, what is its angular velocity in radians per second? So here they're just wanting us to change the units. So we're just going to be doing dimensional analysis. But the fact that it's going clockwise lets you know that this angular velocity is negative. So that's why when we put it in here, we put negative 33 and a third revolutions per minute. And then remember, if we want to get rid of revolutions, we put revolutions on the bottom, and we know that one revolution is 2 pi radians. And then we're going to change our minutes into seconds. And that gives us our answer here. Okay. So that's why I said it's probably a good idea just to commit to memory that when you see that word clockwise, that means it's negative. If you see the word counterclockwise, that would mean it's positive. Okay. All right. So we did angular and linear velocity, or angular velocity. But angular and linear velocity on an moving on an object moving in a circle are related. So if we have on a carousel, for example, this is a carousel. So you're moving in a circle, so you have your angular velocity, but you also have a linear velocity that's related there. Now, linear velocity would be if at any particular moment you it stopped moving in a circle, you would go off, according to inertia, you would just go off in a straight line path and continue to move in the same direction you were moving at that instant. So, at any instant, an object moving in a circle is also moving in a direction tangent to the path, the circular path. Um, so, it would be like if you're going in a circle, and this for some reason broke, then that horse and you would fly off in a straight line path, tangent path, until some other force acted on you and stopped you. So when you're moving in a circle, you have both an angular velocity and a linear velocity. Okay, so let's look at how that works. And they are related to each other. So the relationship is given by this formula. So the object's tangential speed is tangential, meaning just the straight line. So its linear speed is equal to the circumference of the circular path divided by the time it takes to complete that path. So if you could take that circular path and you could lay it out flat, which would just be the circumference of the circle, and you divided that by the time it takes you to go that circumference, that would be your linear speed or your tangential speed. And just to either keep things less confusing or more confusing, I'm not sure which one, they just do time as a capital T in that respect. So your straight line path, your straight tangential velocity, that's why they have VT, tangential speed, TV, is equal to your distance divided by your time. In this case, the distance would be the circumference of the circle, 2 pi r, divided by the time it takes you to go that distance. Okay. We factor out the radius and we put these two things, we group those things together. And remember, if we group those things together, that is the angular velocity. So our tangential speed is the radius of the circle times its angular speed, or the magnitude of its angular velocity. Okay. And that is given in meters per second. Now remember, we said the angular velocity is just per seconds because we're measuring that degrees in radians, which doesn't really count as a unit. But when we convert that to linear speed or linear velocity, it goes back to being meters per second. Okay, because our radius is measured in meters and our angular speed is measured in per seconds. Okay. So make sure you have those things written down and you understand that that is your relationship between linear velocity and angular velocity. Okay, so we've talked about angular displacement. We've talked about angular velocity. We now need to look at angular acceleration. Right. Okay. So angular acceleration would be whether something that is rotating in an object increases the speed with which it rotates or decreases the speed with which it rotates. Just like regular acceleration is whether you're increasing your speed per second or decreasing it per second. And so our formula, we're going to use the Greek letters. If you'll notice that everything angular is using the Greek letter rather than the English letter. Linear is the English letter. Rotationally or angular, it's going to be the Greek letter. So alpha divided by the change in omega over the change in time. Your change in angular velocity divided by your change in time, which of course is seconds to the negative 2, or per seconds squared. Okay. We're almost finished with this section. Probably going to split this up into several videos, but all right, so the sign of the angular acceleration again determines whether the velocity is positive or whether it is negative. So if angular velocity and angular acceleration have the same sign, then the speed of that rotation is increasing. It's spinning faster and faster and faster and faster. If the angular velocity and angular acceleration have opposite signs, that means that the speed is decreasing. That means it's spinning slower and slower, and eventually it will stop. Now, if these diagrams help you visualize that better, then great. If not, then don't worry about them. Okay. Just know if the two have the same sign, then that rotation is increasing. If they have opposite signs, that rotation is decreasing in speed. All right, moving along. Here is a quick example, and this will be our last. This is our last slide for this section. Okay, so here's an example problem. As the wind dies, the windmill that was rotating at 2.1 radians per second begins to slow down with a constant angular acceleration of negative 0.45 radians per second squared. How much time does it take for the windmill to come to a complete stop? So we can see the negative sign indicates that this thing is slowing down. So remember that angular acceleration is the change in angular velocity divided by the change in time. We know we're looking at how long is it going to take to stop. Well, if it stops, that would be zero acceleration, zero velocity, minus 2.1, which is where it started. And then we're going to rearrange this to solve for t, which is what they did right here. Just rearrange this for t. And so that's going to be the change in the velocity divided by the acceleration. Now, remember, we're talking about the time here. So time's always going to be a positive number. So if you did something wrong and came out with a negative number, then you know, okay, I've got my numbers in the wrong place or something, because time can't be negative. Okay. So just as linear speed is equal to the radius times the angular speed, so linear acceleration. So remember, there's a relationship between angular velocity and linear velocity. There's a relationship between angular acceleration and linear acceleration. And you need to make sure you understand that relationship. And here it is right here. So the tangential acceleration, that's why they're doing alpha t, the tangential acceleration is equal to the radius of the circle or radius of the path times the angular acceleration. Okay, just like the tangential velocity was equal to the radius of the path times the angular velocity. Okay, so just make sure you understand that relationship between those two. All right, let's see if we have any. Nope, that is it for section 1. All right. If you have any questions on this, make sure you bring them to class, and we'll be working more example problems in class together.